Assalamu alaikum. This is Shakar Hussain, ID 162002023, Department of CSA. Assalamu alaikum, sir. Thank you so much for giving me this opportunity for presenting today's presentation. Today, my presentation topic is procedure of what is the procedure of random and serial counter with an example. So, in this case, I would like to share my content index with you. What type of context I index here? Firstly, I would like to introduce what is the digital counter. Then I will express about overview of serial counter. Then of course overview of random counter, procedure and example. In this slide, I will show a example of a random counter. Then as we will go for as the conclusion. So in the introduction slide, I would like to express my knowledge about the digital counter. What I know, a digital counter is a fundamental electronic circuit that sequentially counts and represent numeric values of binary form. We already know that. It is commonly used in digital electronics and pulse technique for various applications, including timekeeping, frequency division, and data processing, which we shown as our lab class. Digital counters can be designed using flip-flop and logic gates, offering efficient and reliable counting capabilities. So this is the work functionalities of an digital counters. So next, here we know that there are two types of counter. One is serial counter and one is random counter. We design as like our wish, which counter we have need as a serial counter or digital counter. So in this serial counter, I would like to say perspective of my knowledge about serial counter. A serial counter is a type of digital counter where flip-flop are connected in series, allowing one flip-flop to toggle on each clock pulse. Okay, it is straightforward to implement but has slower propagation delay due to the cascaded structure. Serial counters are commonly used for basic counting tasks in digital electronics and pulse techniques. Here are the sample diagram of serial counter. What is here is physical structure of circuit design. Then I would like to express here the overview of random counter. A random counter generate non-sequential and unpredictable count sequence. That means we choose any number of serial as our wish to design our random counter. It can be any number for designing the random counter. Okay, then unpredictable count sequences using feedback mechanisms. It is useful for applications such as cryptography, pseudo random number generation, and digital games, providing random behavior and various purposes. We know that today current world is very realistic and real time. So here can be any perspective, any situation in digital electronics device, logic device can happen. So here, that's why we need to a random counter for designing the logical device for getting the appropriate output, digital output. It can be analog to digital, digital to analog. Okay, so very interesting and important thing is that is very crucial. I would like to say that what is the procedure of designing a counter, especially random counter. We know that serial counter, it's the sequential counter, we can say, and we know that already. Serial counter, we can say it's sequential counter. That means the getting number will have sequentially come and design in the counter. In this random counter procedure, there are 5 to 6 step procedure here. Firstly, we have to determine that number of flip-flop. So how we could determine the number of flip-flop? We know that in our random sequence number, which is bigger among them, which is big number among them of getting a random number, this number binary conversion will be the maximum or number of flip-flop in our counter designing part. In the maximum number, when we convert in binary, that means digital conversion, which number is applicable for represent the numeric number 3-bit, 4-bit, or 6-bit, etc. Like usually we taking 3-bit. It can be any number of bit. So how number it bit required to represent the numeric number in digital conversion, that means binary, that number of flip-flop we need to design this counter. So the procedure of designing a random counter involves selecting the number of flip-flops, determining the feedback mechanism, defining the set value, and implementing the feedback logic to generate non-sequential and unpredictable count sequence. So after determine the number of flip-flop, we have to create an excitation table. We will how to create excitation table, we will show in our example part. So then we have to draw the state diagram. After that, we have to create state table. Then we have to, for design the counter, for design the circuit design counter with flip-flop, we have to get simplification of JK flip-flop. So that's, it can be any flip-flop, but generally in general we design counter in JK flip-flop. We have to function simplification of K-map, that means Karnaugh map. We know the rule of Karnaugh map, how to simplification it by sorting. So we will see it our example part. So here we will now see an example about random counter, how to design. Here we get 3 number, that means 0 1 2 3 0 1 2 3 0 1 2 3. Here maximum digit is 3. Convert binary, if we convert 3 in binary, we will get 1 1. We know the how a decimal or numeric number convert in binary and what is its position. We know that the first position of 1 is value 1, second position 1 is value is 2. The addition of 2 number is 3. That's why here we get the decimal 3 number representation or conversion in digital number, digital conversion or binary representation in 1 1. So after that, we have created to excitation table. In this random sequence, we will represent the counter by JK flip-flop. That's why we have to take the, we have to apply the excitation table of JK flip-flop. We know that what is the functionality of JK flip-flop. When 0 0, that time we get 0 0 x 0 1 1 x 1 0 x 1 1 1 x 0. So after that, we know that the circuit diagram of JK flip-flop here, we know that there are 2 type of counter, asynchronous sound counter and synchronous sound counter. That's why we need here a clock to represent the JK flip-flop. So here the representation of JK flip-flop status. When we get 0 0, that time hold. When 0 1, that time we 0 reset. We know that how to prove it. We are see these functionalities in our classroom. We discuss over this topic. So when we get J1 and K0, that time 1, that means set. And when we get J1 and K1, that time we get toggle mode. So we know that here is very simple how to create the excitation table. Here is a very logical things that first we have to create 0 1 0 1 don't care. Then we have to get again, don't care and 0 1. So in the forward of slide, I'd like to say we get our we know that we have to take a single repeat of the random counter number. Here we 0 1 2 3 4 type of random sequence we have we are getting here. So that's we convert the number in binary mode. We know that what is the representation of binary for this random numeric number. So then we have to apply the fourth. We have to apply the fourth procedure of the counter design procedure. Here we have to take first present state, then we have to in the next step we have to take the next step. What is the functionality happened here? In the present state means the first number 00 here, and next step means after that number the binary representation of 0 1, then 0 1 to 1 0, 1 0 to 1 1, and 1 1 to 0 0 here. So we know that we have to now calculate the input of JK. We know that here is 4 number, that means 2 representation JB KB JK. So here we according to the excitation table here of JK flip flop, we have to take first B. B we here seen that 0 0 0 0 means here we have to take the excitation according to excitation table 0x, then 0 1 1x 1 0 x means I mentioned the don't worry expression. Okay. 1 1 equal to x 0. Here according to the excitation table we have to put on the JK JB and JK values. Then here we have to, as I mentioned that before, we have to simplification using by Karnaugh map procedure. Here after getting the after putting the position of those values in K-map, we get JB is equal to A, KB is equal to A, J is equal to 1, and K is equal to 1. So we know that how to design the K-map and how to procedure and getting the what is the getting procedure of value of every and each product, that means JB, KB, JK, and as like as applying the K-map, here we get the value of JA, KB, JB, K. Okay, after that's the core and final representation of design the random counter here. We already mentioned that our maximum numeric value was 3. That means there was a binary representation was 1 1. That means we need 2 flip flop here for designing the counter. That means here we took 2 JK flip flop here. One is LSB and one is MSB. And here JK JA, we know that we have to, that means it's synchronous counter. That's why we have add the clock according to synchronous. That means at a sequence. Okay, then we have to putting that those value which we getting in the procedure by K-map. Here we already have taken the value of JB. JB that means JB in the K-map, JB equal to we get A, and JB is equal to we get here LSB portion. We getting this, we connect this value with JB, and j is equal to we getting 1. We putting this value in 1. Okay, that may and k1 ka is equal to 1 and kb is equal to a. And after all the getting result and putting the connection according to the KMap result, here we have finished our random counter here using by two flip-flop circuit, and JK flip-flop we are using here. And we know that there are two type of counter, up counter and down counter as like as. And here I would like to say that the difference between the serial counter and random counter, it's mean the in the random counter we can choose the value as like as our wish. Any type of number, any type of decimal number we have can choose for designing our counter. And in serial counter, there have must maintain the decimal sequence of the value or any type of sorting number. That's the main difference of serial counter and random counter. So as like a same procedure, we can design the serial counter, but the difference is that there are in serial counter is a sequence of number, and in the random counter is the number is come to by random, and any number come any position. That's the factor here in counter. So in conclusion, I would like to say as the assumption of a serial counter and random counter, digital counters play a crucial role in digital electronics and pulse techniques. We know that the 21st century we are just knocking the door of fourth revolution, that means IT revolution, information technology revolution. And here the digital counter play a big and crucial role, enabling precise counting and sequencing operations. Serial counters offer simplicity for basic counting tasks, while random counter provide unpredictability for application like cryptography and random numbers generation. Understanding the design procedure of these counters is essential for efficient and reliable circuit implementation. That's my presentation about serial and random counter. Thank you so much, sir, for giving me this opportunity. This is my great honor, and I feel very pleased.